In this lesson, we take what we've learned about Faraday's law and we apply it to AC or alternating current generators. Here are the objectives. Now, the principle behind an AC generator is that we're going to take a loop of wire that's sitting in an external magnetic field. Let's say the magnetic field is going in that direction, and we're going to rotate it. And because the flux through the loop is given by B, the magnetic field strength, multiplied by A, the cross-sectional area, multiplied by cosine of theta, where again theta is the angle between the normal to the loop and the magnetic field, as I change theta, I'm going to change the flux. And remember that Faraday's law tells us that if we have a changing flux through a loop, then we have an EMF that's generated. So that's the basic principle underlying AC generators, which are the kind of generators that generate the power that's delivered to your house and that you get when you plug something into a wall. Let's take a look at an animation now to see how this works. So here's an animation. We can see that we have a magnet. This is the North Pole and this is the South Pole, as you can tell from the magnetic field lines which point from north to south. And inside it we have this rotating loop of wire indicated by the red lines. And here's a loop of wire and it's connected to these two rings. I'm going to pause this for a moment. And let me actually make that go a little bit further so that you can see that this wire here that's currently on the bottom extends and does not touch this ring but touches this ring right here, while this part of the wire touches the first ring. So each wire stays connected to the same ring throughout. You might be able to see that better now as I keep the animation playing. And the loop keeps rotating. Also notice over here that we have an EMF that's being generated that's alternating back and forth from one extreme to the other and passing through zero in the middle. And that's graphed here at the top. This alternation is what leads to the name alternating current. Now let's try and understand a bit better what's happening here. So here we have the same kind of setup seen from a different angle. We have a north pole and a south pole of a magnet, and we've got a loop of wire that's rotating within the magnetic field. If we take a look here at the indication, you can see that there's a handle that we are turning to make this rotate, and the handle in this part is going downwards. So if we want to use our conventions for our direction into the page, we could say that this whole wire here, this whole wire is moving down into the page. That's what I mean by these X's. It's the wire itself that's being forced down into the page by our turning of the loop. And this one here is moving out of the page towards us. So the line segment or the wire segment AB is coming out of the page towards us, and CD is going into the page away from us. Notice here that AB is connected to this ring. So AB is connected here, and CD is connected to this ring over here. CD passes right through, doesn't touch here, and goes to this ring over here. If you take a look later over here, you'll see that AB is still connected to this ring. So I just want to point that out, and CD is still connected to this bottom ring over here. That's going to become important in a moment. Let's come back over here. If we now think of a positive charge that is sitting in the wire AB. So we've got a positive charge in the wire, and that positive charge is being forced out of the page towards us, and it's sitting in a magnetic field. So using the right hand rule, we point our fingers back towards us because this positive charge is moving out of the page. We point the palm of our right hand towards the right in the direction of the magnetic field, and our thumb is left pointing upwards in this direction. That means that the force on this positive charge is going to be upwards towards B. If we do the same thing over here between CD, so take a positive charge here, it's now being forced by this mechanical turning that we're doing by turning the crank. It's being forced by that to go down into the page. Point your fingers therefore into the page in the direction of the velocity of this positive charge. Turn your palm so that it's pointing to the right, and that again leaves your thumb pointing in the direction of the force. Here that force is downwards. So you can see that we're going to have, as a result of the forces on these positive charges, a current here that is going clockwise around the loop. And if we follow that out of the field, then we can see that the current here would go C to D, it would pass right through here, remember it's not touching this ring, and then it would go in this direction. And if this is a load, like a resistor or a bulb or something like that, it's passing in this direction through the load, and then up here through this ring, and then up through A and B. Now if we follow this a little bit later, now we've got the CD segment has been rotated around. So we've swiveled this around and CD is over here, and now CD is coming up on this side. So this section CD is coming up, and now A and B are going down into the page. The magnetic field is still oriented in the same direction. And so if we repeat the process, we look at a positive charge here, it's being forced out of the page towards us. We use the right-hand rule, and that tells us that the current is going in this direction. And using the right-hand rule again here, now we point our fingers into the page, palm to the right, and again we get a current in this direction. However, this wire AB is still connected to this inside ring, and so the current here goes like that, and from CD it's going to come back up and through here, not touching here. So if you follow that around, you'll see that now the current is passing through the load in this direction. And so again, this is an alternating current that is shifting back and forth in the direction that it is going through this load. Let's take a look again at the animation now to put this all together. So here we are back in the animation that we used at the beginning, and now we've got a rotating loop of wire in an external magnetic field, and we've seen that we can use the right-hand rule on the positive charges in the wire at any point in this rotation to work out the direction that the current is going to travel around the loop, and then through these ring connections, the direction that the current is going to travel around the rest of the circuit. And we see this voltmeter showing an alternating potential, an alternating EMF that's going backwards and forwards. Again, what this is doing is it's taking the mechanical work that we are putting in here and turning this crank and is turning that into electrical energy. So this is the principle behind an AC generator. Let's keep thinking about that loop of wire turning in an external magnetic field and think about how the flux through the loop and also the EMF are changing as a function of time. I'm going to imagine that I have a magnetic field that is pointing from left to right across the page. And I'm going to draw a side view of the loop of wire that is rotating in this field. So here is the loop at the start, oriented like this, and I'm going to define this as the positive direction for the normal to the loop. And it's going to rotate in this direction, clockwise, and so a little bit later, well, let's say halfway through the time, this is time on the x-axis, halfway through the time it's going to be back in an up-down orientation like this, but the normal pointing that way, and then after a full cycle, it'll be pointing like that. And now I can fill in the parts in between. If we imagine it's rotating like that, now it's pointed like so, and like this. And I won't draw all the arrows, but you can imagine that it's going to be oriented like this in between the times. Again, what I've got here in perspective is I've got a loop of wire like that I'm rotating around, and I'm just looking at this edge and the orientation of this edge to signal me as to what's going on. Now, if I think about the flux, let's draw the flux, magnetic flux through the loop in green here. Here I have maximum flux through the loop. Here I have zero flux through the loop. The magnetic field is pointing left to right, and none of it is cutting through the loop because of this orientation. Over here I have maximum flux through the loop again, but again now the field is pointing left to right, and the normal of the loop is pointing right to left, and so this is maximum negative flux if we're being mindful of our directions. Here I have zero flux again, and here I have maximal flux like this. And you can see that if you join these and imagine interpolating the points in between, then I get a cosine curve. Something like that. So the flux is changing as a function of time in this cosine shape way. Now let's think about the EMF. Remember that Faraday's law tells us that the EMF is equal to the negative time rate of change of the flux. If you know a bit of calculus, you know that another way of stating that is that it's the negative of the derivative of the flux with respect to time. These lowercase d's are just the calculus way of replacing the deltas to mean change, but change when we get infinitesimally small. So again, if you know calculus, you might know that the derivative of a cosine graph is a negative sine graph, but with this negative here, a negative of a negative is a positive. So that would tell us that the EMF graph should look like a sine graph. So here is our EMF graph as a function of time, graphed over top. And I'm drawing them here as if they have the same amplitude, but they don't necessarily have the same amplitude. I'm just doing that for convenience. Another way of thinking about this and getting the blue EMF graph from the green flux graph is to just do what taking the derivative is doing. It's taking the slope of this graph, so here the slope is 0, and making it into the y value of the blue graph. Here the slope is maximal and negative, but that negative means that a negative of a negative is a positive, and that's how I get that, etc., etc. So the blue graph, which is the EMF, is the negative of all the slopes of the green graph, which is the flux. Again, Faraday's law tells us that the EMF is given by the negative time rate of change of the flux. So this lesson has looked at the principles behind AC generators and how you can generate an alternating current by rotating a loop of wire in an external magnetic field.